Welcome back to another session of our Inspire seminar series, which is focused on synchrotron and synchrotron adjacent research. This is a session that is running on alternating Wednesdays from 1:30 to 2:30 on Zoom. And if you have any suggestions for speakers that you feel would be interested in presenting their research, please let us know and we'll see if we can invite them on. So for today, we have one speaker. He'll be speaking for 50 minutes, and then this will be followed by a 10-minute Q&A session. For anyone who is attending, please keep your video and mic off during the presentation. This is to reduce bandwidth and distractions. If you have tech issues, please let Ardalyn or Lenore know. And if you have the questions for any speakers, for the speaker, you're welcome to put them in the chat while he's speaking, and I can read them out to him after he's done presenting. And if you want to hold onto your questions up till the end, then feel free to do so, and you can ask him yourself. So for today, I would like to present Dr. Robert Green as our speaker. He is an associate professor in the Department of Physics and Engineering Physics at the University of Saskatchewan, and he will be presenting on synchrotron studies of advanced materials for next generation technologies. Robert Green, the floor is yours.
All right, thank you, Linda, and thanks for the opportunity to speak today. Today I'll be speaking about some research that we've been doing over the past several years. I've kind of picked and chosen some topics that I think will kind of have more of a broad appeal. The physics isn't too intense, and I can explain them at a level that I think everybody in this diverse audience should be able to follow. So that being said, if any questions come up along the way that are related to kind of not fully understanding what I'm talking about, definitely feel free to interrupt me. My goal here is to not lose anybody along the way. I'd like everybody to follow along with what I'm talking about. So I'd like to begin with a little bit of motivation in that, while this talk is about studying materials for next generation technologies, and I think it's interesting to reflect sometimes on just how far technology has come, whether it's over the past few years, the past couple of decades, or the past century. Just how different our lives are now compared to how they were previously. And so I've got a picture of a smartphone here. Many people have smartphones these days, and it really it provides you with a lot of good things, a lot of distractions as well, but a lot of good things in that on one hand it connects you to the internet, and I think it's easy to take for granted the knowledge and the information that we have at our fingertips if we have a quick and stable connection to the internet. There's so much information to be quickly looked up, and of course it allows us to communicate at sort of unprecedented levels, right? We can instantly video chat with anyone around the globe, or have live meetings such as this, where we're all kind of sharing video together and interacting almost seamlessly as if we were in the same room. And then, of course, another aspect of modern technology that is really kind of becoming abundant or more ubiquitous in recent years is artificial intelligence. So we hear terms like machine learning or artificial neural networks so often these days, and it brings really a new power to technology and computing. Things that were traditionally very difficult to do in sort of the old style or the more traditional style of computation, like image recognition, so facial recognition, translation between languages. These are things that can be done at a much higher level using machine learning methods and artificial intelligence. And then, of course, self-driving cars, which are, becoming closer and closer to, well, I mean, they are a reality in some parts of the world. They're just not quite ready for Saskatchewan roads yet, I don't think. But all of these things are kind of made possible by advances in AI in recent years. Kind of reflecting on these things, you can sort of think about some modern day conveniences. I know from my perspective, things like home automation and monitoring are are kind of almost game changing. I'm the type of guy that if I go away on a trip with my family, I'm always kind of stressing about, do I have a water leak at home? Is my house flooding or something like that? But now with home automation, you don't have to bother your neighbors to get to check in on your house. You can monitor things remotely. Of course, GPS and navigation we have in our smartphones, so we almost, it's very difficult to get lost these days, whereas 30 years ago it was more commonplace. And then, of course, with driving in itself, the current generation of automobiles, typically most have lane assist or adaptive cruise control, so you don't even have to worry about slowing down. If you come up behind somebody on the highway, your car handles it for you. Blind spot detection is quite helpful in the city. Of course, you don't want to rely on it too much, but it's certainly a helpful convenience. And then I'll mention again that we're getting closer and closer to sort of a large scale implementation of self-driving cars, which is should be a very good thing. And then, so of course, like I say at the top, modern technology is remarkable. For us who all have this synchrotron connection, we can even monitor the status of the synchrotron beam from our smartphone these days, which is nice and convenient. We typically like to see more yellow than this, but this happened to be the situation when I captured this last night. Possibly now getting into the realm of almost scary, but still interesting, is that modern technology can even tell you why it's remarkable. So if you've heard of these large language models like ChatGPT, which has sort of captured the public's interest in the past 6 months. So these are artificial intelligence that you can chat with, and which have been trained with large amounts of data, and which can answer questions, solve problems, do things at quite a remarkable level. So, just for an example, I asked ChatGPT what makes modern technology so remarkable, and it gave me a well-formatted and clear and quite an extensive answer as to why modern technology is so remarkable. And if you haven't heard of ChatGPT or haven't looked in it, I encourage you to take a look. It's an incredibly powerful artificial intelligence. And well, for myself as an instructor of undergraduate and graduate courses, it's a little worrisome. I know some of my engineering physics courses, I can upload assignments into ChatGPT, and it can give me an almost perfect solution to those assignments. So it's certainly something that as instructors we have to worry about in the future years. But at the same time, it's quite amazing how good it is and how powerful it is. Okay, so these are a couple slides about modern technology, how far we've come, how great it is. But now I'm interested in looking forward to the next couple or few decades. What might be coming ahead? And to do that, it kind of helps to look backwards. So I want to start by talking about what made today's technology possible. And it's somewhat of a subjective question, but you can certainly trace it back to the invention of the transistor, right? Because all of this modern day electronics operates based on utilizing transistors. So I have a picture here of the very first transistor ever invented in 1947 in Bell Labs in the United States. And so this is a transistor where the small triangular part there has dimensions of roughly 1 centimeter on each edge. And well, for the purposes of electronics, a transistor is just an electrical switch. So you can think of a light switch in your house. You turn it on, you turn it off. A transistor is a switch like that, but that you can turn on and off with an electrical signal. So it's all electronic. There's no mechanical, there's no moving parts necessarily in a transistor. And that's what makes it sort of a game changer. Now you can build a computer processor out of all of these interconnected electrical switches, which can perform the computations in the processor. Okay, so like I said, it's an all electronic switch. Transistors are also amplifiers. So for that third switching signal, you could imagine putting in any sort of electronic signal, whether it's an audio signal or some sort of analog visual signal. You could put it into the transistor and it can amplify it. So this is important for long distance communications, for example, where you need to amplify a signal. But for kind of the purposes that I'm interested in, it's the transistors that perform the actual number crunching in our computer processors and our smartphone processors. Actually, in each one of our smartphones these days, we have several 100 billion transistors, which is quite remarkable to think about. That going from this device, which has roughly 1 centimeter dimensions, nowadays transistors have roughly 10 nanometer dimensions, and there's on the order of a few 100 billion of them in each one of our smartphones. They are also used now, if you're familiar with the concepts of a hard disk drive versus a solid state drive for your computer memory, the solid state drives utilize a form of the transistor to store your data. So not only are they used for the actual processing of the data, but for storage as well. And then, like I said, they amplify signals for communications. But for the interests or the purposes of this talk, you can look back in history and kind of see how the transistor was invented as a result of advances in material science. And what do I mean by that? Well, if you look at the period from the 1920s to the 1940s, we had the development of quantum mechanics. So this is roughly 1926, 1927 by scientists like Schrodinger, Heisenberg, Paul Dirac, Max Born, etc. Once we had the theory of quantum mechanics, it allowed us to understand what's going on in materials at the nanoscale level. So what are the electrons in a material doing that allow it to maybe conduct electricity versus not conduct electricity? What's the difference between an insulator and a conductor in this microscopic point of view? Once we had that understanding, we could then understand where semiconductors come from. And I won't go into too much detail regarding what a semiconductor is, but transistors are made out of semiconductors, and they rely on the physics of a semiconductor being able to tune how well a semiconductor conducts electricity via electric fields or doping of atoms or injection of carriers. This whole field of semiconductor physics was born out of our understanding of electronic structure. And then finally, there was sort of an aha moment in, I believe, 1939, that yes, we should be able to, now with our understanding of semiconductors, we should be able to build a device that would eventually be called the transistor, that could be used as our electrical amplifier and our switch. At the time, there were devices that could do this, that could sort of amplify signals and technically be used as switches, but these were vacuum tubes, which were much larger things, used a lot more power, and were much less reliable than the transistors we have today. And so it was the invention of the transistor that sort of set off the electronics revolution and ultimately led to all of the technology we have today, the things that I mentioned on the previous slide. So then the question arises, what's next? Okay, today's technology was born out of the transistor and all of the everything we've built upon on top of that. What do we see in the near horizon? Well, today's artificial intelligence, or a large portion of it, is based on the idea of mimicking how a biological brain computes. Okay, the concept of an interconnected set of synapses and neurons that can perform this type of computation that we would call neuromorphic computation. But what we're currently doing today is we're just building these artificial intelligences in software and running them on a conventional computer. And that's really quite inefficient. If we can build a computer, the hardware of a computer that is more like an interconnected set of synapses and neurons, then we'll be able to sort of deploy artificial intelligence at a much wider scale, and nothing necessarily extreme, but just certain types of computation, right? You could envision a self-driving car having a processor that is a dedicated neuromorphic processor, which allows it to operate much more efficiently, use less electricity, etc. Us humans, in terms of our computational abilities, are extremely energy efficient, right? A human doesn't expend a lot of power in the traditional sense. I think a human brain uses roughly 20 watts of power to do our most intensive computations, whereas a comparable supercomputer that can compute at the capacity of a human brain would use on the order of megawatts of power. So there's quite a difference in energy efficiency in there. So there's a big effort right now to try to build neuromorphic hardware, and we need new devices in that sense, something different than a transistor. And so we need different materials to build these things out of. Another thing you've likely heard about is quantum computing. So now this is sort of, it's an entirely new approach to computing where we're leveraging the power of quantum mechanics. And we can have quantum algorithms now that can solve problems in a short amount of time that would have taken a conventional computer thousands or millions or billions of years to solve. So it will sort of open the door to solving a new set of problems. And for somebody like me, the exciting thing about quantum computing is when we're trying to understand how a material behaves the way it does, and we're doing physics at the nanoscale of what's happening in the material, the physics and the mathematics gets very complicated. We're always having to make approximations, and in many cases, we can't quite understand why a material behaves the way it does. But if we can simulate that quantum material on a quantum computer, we'll be able to model these things much more quickly and accurately, and ultimately understand where interesting properties come from and how we can further harness them. Another sort of up and coming field is spintronics, and I'll talk about this a little bit later today. The idea is, well, our conventional electronics are ultimately, the namesake is the electron, right? Because we're moving electricity around in our electronic circuits. In spintronics, instead, we're essentially moving electron spins around in our spintronic circuits. So if you're familiar with the concept of an electron having a negative charge, but also this other property called spin, we don't have to get into too much detail what exactly it means, but it's just another characteristic of an electron, and we can use that for computation in spintronics. And it's been shown that we could build, analogs to what our current electronics are, but that use much less power and are faster than our current electronics if we could leverage the electron spin. A couple of things that are particularly important in this realm of problematic climate change and needing alternative energy sources, on one hand, is enhanced energy capture. So I'm thinking in terms of solar energy capture. Our current approach to solar cells and photovoltaics is based on silicon. And that paradigm has sort of an upper limit of efficiency of 30%. So essentially, only 30% of the energy that comes from the sun that lands on your solar cell can you actually capture in your silicon-based solar cell. So there's certainly motivation to look at alternative forms of solar energy capture, and maybe very different materials and very different mechanisms for converting that solar energy into electricity. And then similarly, as if we transition to more of an electrical based society away from fossil fuels, we of course need ways of storing energy more efficiently, maybe higher energy density in our storage. And of course, we have very good energy storage these days in terms of lithium-ion batteries, but we should always be looking for the next best thing. Is there something that can store energy at a higher density, maybe is more environmentally friendly than lithium-ion batteries? There's certainly room for advances there. And then the last thing is data storage. So with all of the growth of technology in recent years, there's also an exponential growth in terms of the amount of data that humankind works with on a global scale. And so we certainly need enhanced data storage capabilities, and it would be great if we could store data with higher energy efficiency, so less energy consumption in our data storage. And I'll talk a little bit about that later on. So to realize all of these things that I say are going to become, they're going to be relevant in the next couple of decades. In many cases, we need new materials to actually realize these developments. And so I'll talk about a few synchrotron projects today that all kind of relate to this idea of discovering new materials with enhanced functionalities that can make these things come to fruition. Now, the common theme in almost all of my research is the 3D transition elements. And these elements, I argue, have a lot of untapped potential. Well, first off, what are the 3D transition elements? They're these elements here in the periodic table. And I've highlighted specifically scandium up to copper on the right. They have very interesting properties, and they tend to form compounds that can do some unique and interesting and potentially powerful things. And just as an example, throughout history of some sort of flagship 3D transition element compounds, the very first known magnet, a few millennia ago, was known as lodestone. It was just sort of a mineral that was discovered that would attract other. You would feel this strange force between different objects. This was iron 304, now known as magnetite, then known as lodestone. It was discovered about 500 BC. So our first known magnet was based on iron, which is one of these 3D transition elements. Going forward a couple millennia, the first verified antiferromagnet was manganese oxide. And I'll talk a little bit about antiferromagnets later on, but the idea in an antiferromagnet is it's a magnet, just like iron 304 would be, but it just so happens that if you go down to the microscopic scale, there's magnetic fields pointing in opposite directions that end up canceling each other out. So you end up having this thing that is magnetized, but that actually isn't really attracted to anything. So it's not like your typical refrigerator magnet. But these are potentially very useful materials for things like spintronics and data storage. And then if we fast forward a few more decades, we have this complicated compound here, barium lanthanum copper oxide, which was the first discovered, or one of the first discovered, high temperature superconductors. So you've likely heard of the concept of a superconductor. It's something that conducts electricity without any energy losses, so with zero resistance to the flow of current. But typically superconductivity sets in at very low temperatures. We were used to seeing superconductors anywhere below, say, 20 Kelvin in temperature. So extremely low temperatures. But with the discovery of these new copper-based superconductors, now we have superconductivity up to about 150 Kelvin in this family of materials. And while superconductivity would be an extremely useful thing if we could get it up to room temperature, so that in our everyday devices, our everyday wiring, if it were superconducting, it would be an incredible breakthrough. But this class of materials in general, based on 3D transition elements, exhibits just a very vast array of properties and finds uses already in a lot of different applications. Okay, so anything from high temperature superconductivity to all these various forms of magnetism. Actually, already today, they're used in lithium ion batteries as the cathode materials, and all the time, while they're used in photocatalysis as well, and all the time we're looking for new applications that can kind of harness the interesting properties of these materials. So, this is a synchrotron talk. How do we probe these materials using synchrotron X-rays? Well, this class of elements, from scandium up to copper, have very strong resonances to synchrotron X-rays. And well, what do I mean by that? There are these absorption resonances that happen at different energies for different elements. And this in itself isn't unique to transition metals. This is the case for any element, any atom of any element. But I'll show here just an X-ray absorption plot scanning a wide energy range for a material that contains a lot of these different elements. And you see an absorption resonance just below 600 electron volts for chromium, one just below 800 electron volts for cobalt, one around 850 for nickel, and then copper, and then ultimately zinc. So these the atoms based on transition elements in these materials will absorb X-rays at a characteristic energy for the given element. That's the only takeaway from the slide, and it might seem very simplistic to the synchrotron experts here, but I just want to give an understanding of why we might use X-ray absorption and how it might provide us with good information about a material. The kind of sharp spikes you see here are specifically what we call the resonances. And if I were to zoom in on those, you would see kind of a fine structure of various peaks that carry information about the specific state of that element in the material. And so I kind of show that on this slide here. The fine structure around the absorption element carries information about that element. So I have a plot here of two very similar materials, strontium titanium 03 and lanthanum titanium 03. And we're looking specifically at the titanium resonance. So titanium is atomic number 22. It's one of the 3D transition elements. And here you can see, almost immediately a very different structure for how these two materials absorb X-rays at this titanium resonance. And just to be, extremely clear here, where you see a strong peak, that means your material is absorbing X-rays more strongly. If we were together in person, and this could be more interactive, I would maybe ask what is different about these materials. The answer here is the oxidation state. So titanium in the first material is in a 4+ oxidation state, and in the second material, it's in a 3+ oxidation state. So you can see now, okay, on the previous slide, we have sensitivity to the different elements. We also have sensitivity to the specific electronic characteristics of the elements. And here I'm showing oxidation state, but even the way that the element bonds with its neighbors, any sort of magnetic interactions of the element, all of these things leave some sort of fingerprint in these absorption resonances. And this is, to a certain extent, unique to these 3D transition elements. I don't think there would, certainly there's a large or an enhanced sensitivity to these effects at these resonances. So how can we probe these resonances? Well, I showed on the previous slide just simple X-ray absorption. So on the left here, we could have a synchrotron X-ray beam incident upon our sample. We could measure how it's absorbed, and we could measure that as a function of energy across the resonance, and we would gain information about our sample. And we can certainly leverage the fact that different elements have their resonances at different energies, and the shape of the resonance carries information about what's going on in the material. And so a good aspect of X-ray absorption is that I might be studying a material, and here I've just sketched some atoms where maybe my atom of interest is like almost an impurity in the material. It's something at a very low concentration, and seeing what's happening with that particular atom might be difficult with other techniques that are just kind of studying your material as a whole. But if I can tune to the resonance of this particular orange atom, then I can get a strong signal of what's going on with that atom inside my material. Now, it has to be more than one atom, but we can deal with concentrations of atoms below 1%. We can also study not just the absorption of the X-rays, but different ways that they interact with the material. So in the middle here, I'm saying we can study how X-rays are reflected from our material. So we have an incoming beam of X-rays at some angle with respect to the surface, and then we measure how the X-rays are reflected. And where this becomes particularly useful, and again, we can scan the same resonance energies, and we're still interacting with that absorption resonance. I won't get into the fine details, but actually the absorption resonance relates now to the refractive index of the material. And we could study maybe materials in a depth dependent fashion. So I might have a material that has just one layer of special atoms, for example. Well, how do you probe one layer of buried atoms within a material? Well, reflection is a great technique for that. And I'll talk as we go on about a specific example of studying X-ray reflection. And then another thing we can do is study how the X-rays are diffracted. So when you have some particular type of order in your material, whether it's just the order of the atoms in the crystal, or the order of the electronic charge within your material, or the order of magnetism within your material, you can tune to a resonance and maybe see some particular type of ordering. Maybe even a type of ordering that you couldn't have seen in any other way, because maybe it's just an ordering of a little bit of electronic charge. Maybe every one of these atoms is a titanium atom. And so with conventional X-ray diffraction, I might not have been able to distinguish this secondary pattern of orange atoms. But maybe there's a slight shifting of charge between the orange and blue atoms that shows up at the absorption resonance energy. And then I can study it using this technique. Okay, that's basically all I want to say about the synchrotron science, and you'll notice it was at a pretty simplistic level, but that's really all you need to know to follow along with these examples as we go on. And also feel free to interrupt me if you have any questions as I'm going along. So let's look at an example where we're using X-ray absorption to study some new advanced material. And this will relate to the field of spintronics. So in each one of these examples, I'll give a little bit of background. So here we find that if we introduce a small amount of iron into this compound, indium oxide, we don't need to know much about that compound, but we know that if we introduce a small amount of iron, we can induce magnetism in this material. And so while indium oxide is a semiconductor, the result then is a magnetic semiconductor, and this can be used for spintronics applications. And this is shown on the right, where we're plotting the degree of magnetization per iron atom as we increase the concentration of iron dopants in this material. So if we put 2% of iron in this material, this left blue data point, we see that we get a relatively strong magnetization per iron atom. And then as we increase the iron concentration, the material is still magnetic, but the degree of magnetization per iron atom is going down. Okay, so this is something we can do to observe, what's going on in this material, and it gives us a bit of a hint as to what might be the mechanism for this magnetism. So the question we have then is, how is this thing magnetic at all? What's leading to this magnetism? And then how can we optimize it? If we want to move forward with building spintronic materials out of this. This is an example where we have a low concentration of iron. If we can probe it directly, that might give us insight into what it's doing, and we can use X-ray absorption to do that. So let's probe this iron directly. And actually in this project, we came up with kind of a unique way of measuring accurate X-ray absorption. So it turns out with these energies of studying these resonances of transition elements, your X-rays have a relatively low energy, and they only probe, on the order of 100 nanometers into your material. So it's very rare that you can ever measure absorption in transmission, by measuring actually how many X-rays get through your material. In this case, our material was a thin film shown in blue here, and it was grown on top of a thick substrate. And it turned out that the X-rays would go through the film, and then the substrate would glow, it would luminesce, according to, with a brightness proportional to how many X-rays got through the film. So we were able to use the luminescence from the substrate as a sort of transmission detector, because we monitored the luminescence that was coming out, and that's what's shown in this plot here. This peak in this color plot is a luminescence peak, and then the green line scan here shows the fraction of X-rays getting through our sample. So that's sort of the well, it's the negative log of our X-ray absorption signal. So we came up with this unique way, which gave us a very nice quantitative measure of the X-ray absorption. And so then we measured the iron X-ray absorption for these, well, samples with 3 different doping levels of iron, and then one that was not doped at all. And of course, you can see the amount of iron increasing when we plot our X-ray absorption in this quantitative way. But not only can you see the amount increasing, you can see that the structure of this iron resonance is changing a bit. So for this blue curve, the sample with only 2% iron, we have these 2 peaks here that are almost of equal intensity. But then as we go and increase the doping up to the green curve, we have really one main peak with just a small shoulder. So this is exciting because, you know, something's changing in the structure of the resonance between these samples. Can we look at these more closely? Okay, so we take these 3 different iron resonances, and we find that we can decompose them into a linear combination of 2 different spectra. So if I look at this top one here, the red outline is my experimental data. The orange and the blue are these 2 components that I've decomposed it into. And then the black curve is a sum of those 2, which recovers the experimental data very well. And then we find in the different samples, there's different ratios of these different components of these, these 2 different iron component spectra. Now, it turns out, and I won't go into extensive detail here, but I can discuss it after, that the blue curve is indicative of iron in a 2+ oxidation state, whereas the orange curve is iron in a 3+ oxidation state. And so in all of these samples, we have some mixture of iron in 2 different states. Now, because we're doing everything quantitative here, we can quantify how much of each type of iron is present. Now, this plot is a little bit complicated, but let's focus on the orange curve and the black curve first. This is showing us how much iron 2+ in the black curve and how much iron 3+ I have as a function of my iron doping along the x-axis. And then over top of that, I'm plotting the magnetization of the samples per iron atom, essentially. And what we find is that the amount of iron 3+ correlates essentially directly with the degree of magnetization of the samples. So this is telling us that the magnetism is essentially due to the iron 3+, and then we ask ourselves, well, what is special about the iron 3+ that it's leading to the magnetism? This is where we can turn to modeling. So, these line shapes carry detailed information. It's sort of a whole nother degree of complexity, but we can model these line shapes quantum mechanically to understand what's going on. And we find that in the case of the iron 2+, there's nothing too interesting going on. The purple iron atom sort of goes into a site where it's bonding with 6 oxygen atoms, just one of the standard sites within this semiconductor crystal. But for the iron 3+ in orange, we find that this particular spectral signature is indicative of a missing oxygen atom near it. And the material that we're doping these into, indium oxide, is known to have missing oxygen atoms at some site. We call these vacancies. So here we've discovered that the magnetism arises when we dope iron atoms in, and they go into sites that are adjacent to oxygen vacancies. And the reason that this stabilizes magnetism, it's actually understandable. The oxygen vacancies sort of provide, you can think of it as like a conductive pathway that links the magnetism together. They sort of enhance the interaction of the different iron atoms to stabilize the magnetism. So this is great. Using the synchrotron X-ray absorption, we've discovered what leads to the magnetism in this material very specifically, and then how we might be able to optimize it. Is there a way we can grow these materials with no iron 2+? So, we're putting the smallest concentration of iron in possible, and it's all going into magnetic sites. So that might be how we would then go on to optimize this for spintronics applications. Let me jump into another example here where now we're using the reflection of X-rays to study something going on in an advanced material. And so in this case, we're looking at something that is called a two-dimensional electron liquid. So a little bit of background information. We have these two kind of ceramic type of materials, lanthanum aluminum 3 and strontium titanium oxygen 3. Yeah, you can kind of think of them like ceramics. They're electrical insulators. There's not a lot interesting going on with these materials. But it was discovered that if we sandwich them together, really at the atomic level, interface these two materials together, the interface between them becomes conducting. It will conduct electricity because this two-dimensional sheet of electrons accumulates at this interface. So it's really a fascinating discovery, taking these non-conducting materials and forming a conducting interface. And even more interesting, these materials are typically fabricated by growing the lanthanum aluminum oxide film on top of the other one. And as we grow it atomic layer by atomic layer, nothing interesting happens. And then suddenly after we grow 4 atomic layers, this 2D electron liquid forms and the material becomes conducting. Now, almost right away, a theory was developed that could kind of explain how this would happen. But there was this problem in that this theory required that there'd be about 10 times more charge at this interface than was actually detected. So, by passing a current through this interface, hooking it up to essentially a voltage source, we can measure how much charge is there. And one would always find that there's about 10 times less than the theory would predict. So then this question arises, are there maybe some undetectable electrons at this interface, or is this theory wrong? Is this electron liquid forming for some other reason? So we studied this with using the reflection of X-rays, specifically tuned to the titanium resonance, the absorption resonance. And the idea is that, if we were to zoom in on this interface here, there should be some electrons occupying the titanium atoms, and they probably have a slightly different symmetry, at the layer exactly at the interface or as we move away from the interface. Now, what that means for us, well, I showed you, a few slides ago, those example titanium absorption spectra and how they were different for titanium 3+ versus titanium 4+. That's exactly what we'd be looking at here. In the pure substrate here, strontium titanate, we should have titanium 4+. And then in this electron liquid region, we should have titanium 3+. And so if we had some fraction of both, the actual X-ray absorption of each one of these layers would be some linear combination of the titanium 3+ and 4+. Now, the symmetry effect, how the symmetry changes as we go away from the interface, would lead to a polarization dependence in the X-ray absorption of each layer. And that's what I'm showing with the blue and the orange curves, what we would measure with different polarizations of light. And so, this is us just kind of conjecturing what might be going on in this material and how we might do this experiment. And then we would simulate, or we can simulate, what we would hope to see. And so on this energy axis here, I'm showing as we scan our synchrotron X-ray energy across the titanium resonance. And then on this other axis here, I'm showing as we scan our reflection angle, so how we change the angle of reflection of our X-rays. And we should get this complicated structure in terms of the intensity of the X-rays we detect that are reflected. This is the case I'm showing here if there's no electron liquid at the interface. And then if I flip ahead, this is what we would predict to see if there was an electron liquid there. And this is kind of I like this kind of jarring effect, because what we're studying here is really just 1 or 2 nanometers of material that is buried maybe 5 or 6 nanometers below a surface. And we can see this very strong effect in the reflection. This is really taking advantage of the concept of reflection to enhance our sensitivity to this material. So we went and did this experiment, and we studied 3 different samples. And here I'm showing in pink the film on top, and in green the substrate. And then in cases where we expect an electron liquid, I have this yellow layer in between them. And so here I'm showing our reflectivity data in each panel corresponding to each sample as we scan across the resonance and for different reflection angles. And in blue is our experimental data. And then in orange is our modeling of that data with the physical models that I'm showing now on the right here. So for our thinnest sample, this is the nice or the powerful nature of X-ray reflectivity. We can see what's going on in each atomic layer of our sample. And we can see that, okay, the film and the substrate are kind of mixing together to a certain extent, but we don't see an electron liquid, only a small amount of titanium 3+ in this first sample. As we study the thicker samples, they're still kind of mixing together a little bit, but now we see the emergence of this electron liquid. And my length scale here on the x-axis is on the level of angstroms. So we're extracting where this charge is to a precision of angstroms near this interface. Now, the big question, going back a couple slides, is is that theory correct that predicts that there should be a certain amount of charge there? Actually, we see even more than predicted. So in terms of electrons per titanium atom near the interface, we're seeing almost 1, whereas the theory predicted 0.5, and previous experiments would only ever see about 0.05. So that was kind of curious. What we did was we wondered if maybe there were some missing oxygen atoms in these samples, like I mentioned in the previous project. And so what we did was, after doing these experiments, we took the films to actually a furnace near the hexama beamline at the CLS, where we could anneal them in an oxygen atmosphere to try to force more oxygen into the films. And then our data change from the left panel before that oxygen annealing or that oxygen heat treatment to the right panel afterwards. And then what that means in terms of what we extract is this bright green electron liquid from before the annealing is decreased after the annealing. So we're filling in some missing oxygen atoms, that's capturing the excess charge, and then we find essentially exactly within our the level of precision of our experiment, 1/2 of an electron per titanium atom, which was exactly what that theory had predicted. I've got one more slide here on this project that's kind of for the experts. It goes in a little deeper. What we can do is extract details about the symmetry of the charge in each one of the atomic layers. And that's what I'm showing in these plots here for the 3 different samples. And we find, well, of course, the charge occupies the atomic orbitals of the titanium atoms, and we can extract the energies of those orbitals as a function of depth into the sample. And so this allows us now to essentially extract the symmetry of this charged system, which is another aspect that's important for how it conducts electricity. We're currently working on or finishing up a follow-up experiment on this with a slightly different substrate material. My master's student Grant Harris has been working on it, where we're tuning this symmetry effect to change the conductive properties of the material. Okay, I think I'm almost out of time. I had one more example I would go through. I think I'll skip through it. I don't want to go over time. I'll maybe open up for questions at this point. Let me maybe skip ahead to my conclusion slide, because I wanted to pose the question. Of course, we have a very diverse audience here with the Inspire program, which is great. It's nice to get exposure to different techniques. And you might ask yourself, are the techniques, so the absorption, the reflection, the diffraction techniques that I mentioned, useful for your research? And the short answer is maybe. So if you do happen to study 3D transition elements, so these ones in this row from scandium to copper, then I would say almost certainly these methods would be useful for you. And it's because of what I said about those resonances. They contain very detailed information. They're very sharp resonances. They give a strong signal in experiments. If you happen to or study 4F rare earth elements, so down in this series from lanthanum to lutetium, there's also similarly strong resonances at similar energies. And so in that case, I would say probably these techniques are useful for you. If you happen to study 4D transition elements, so for yttrium up to cadmium, maybe. So again, they kind of have similar resonances that tend to be a little bit weaker and maybe don't carry quite as much information. And if you study other things, then I would say there's a chance, and I'd be happy to discuss if you have questions about whether this could be useful for your research. Okay, I have far too many people to acknowledge to list them all out, but I'll maybe just show my acknowledgement slides here. And well, thank you for your attention, and I'm happy to take any questions now.
Thank you, Robert. I am so intrigued about your talk, and it was really interesting to see what all is being studied. And I'm really wondering, it'll be interesting to see how technology will change based on the studies that are being done right now.
Yes, exactly. Things are changing rapidly right now. I'm curious what the next even decade holds.
Yeah, no kidding. So if anyone has any questions, if you're too shy to ask it yourself, again, feel free to drop in the chat, sorry, and I can ask them for you. Or if you want to ask them yourself, either raise your hand with that reaction icon or just ask out loud. Choice is yours. I'll just give a moment in case people are typing.
Maybe I explained everything perfectly. You never know.
Well, your last slide answered a question that I was already going to ask, so I'm already out of questions, unfortunately. While we're waiting, did you want to expand a little bit more on that last topic of yours?
I certainly could. Let me. I can share a slide while we're waiting. It would probably take 15 minutes to explain in detail, but let me just show you the background and the question and then the answer. So there is a type of material based on nickel that has this very interesting magnetic order. So shown here are the atomic layers of a material, and they're kind of magnetized in these orange and green pairs. So if you see the green pairs, you have a magnetism going up and then down and then up and then down, and then the orange pairs going right and left and right and left. So it's one of these materials where if you looked at it from far away, it wouldn't look magnetic because everything cancels out. But if you zoomed in, you would see that it is magnetized. So yeah, just to summarize this into 1 minute, we studied this material to try to determine exactly, there was a question of whether this is exactly what's going on in this material, and also to see if we could get some control over this magnetism. And we did some synchrotron experiments. I'm kind of showing the data here, and now I'm showing the end result, where in the top, we're looking at polarization dependence of the diffraction we did. And then on the bottom, we're looking at these green and orange layers, the magnetization in those layers. And we found that by tuning the thickness of samples, we could actually go between this case on the left, where the green and the orange are going in opposite directions, to the case on the right, where everything's going kind of along the same axis. And the main takeaway then was that we kind of had unprecedented control over this magnetic ordering, and we were kind of switching between two states. And so the idea that arises then is, can we engineer some sort of magnetic devices out of this, whether we're storing data by switching between these states or doing some sort of computation by switching between these states. That's the end result. Like I said, it takes about 15 minutes to explain exactly what we did and how we arrive at this result. But yeah, thanks for asking, Linda. I'm happy to explain that.
That is so cool. So again, if anyone has any questions, feel free to either drop them in the chat or blurt them out.
If something comes up later as well and you want to send me an email, I'm happy to answer, particularly if you're wondering if a project you're working on might have relevance to these type of experiments. I'm happy to discuss that.
Okay, seems a little bit quiet, so I guess you explained everything perfectly.
Wonderful.
So thank you so much, Robert. That was an excellent talk. And hopefully at some point, maybe I can drop by your office and ask some more questions once I've had more time to look at things.
Sounds good.
So next talk will be in 2 weeks, and otherwise have a great rest of your week. Thank you again, Robert.
Okay, thanks, Linda. Thanks, everybody.